this computer. Okay. Okay, so to access the server, you need to go to .ssh folder. Here you have this. I have many files. I also have this config file.
স্যার একটু ফুল স্ক্রিন করে নিলে ভালো হয়।
Full screen or bigger font. Yeah. Is it good?
হ্যাঁ, বেটার।
Okay, so I have this config file. So if you have a public and private key, if you configure your system properly in this config file, then you can access the server using simple command. For example, SSH. মানে আমার সার্ভারের নাম হচ্ছে moment. I just type SSH moment and I'm in my server. So it's really easy. Plus, we also want to have our VS Code, right? VS Code দিয়ে, like, as a text editor, you can do this. Plus, when you generate the bands, you can also see the bands like this. Graphically দেখতে পারবো. So that's useful. There could be other text editors, but somehow I've been using VS Code and it's working fine. So you can use whichever text editor you like. So how to configure this system so that you can just type SSH and a keyword to access the server. So তোমাদের মানে সাথে যদি কম্পিউটার থাকে, কোনো প্রবলেম হয়ে থাকে, জাস্ট ট্রাই টু ফলো অ্যালং। ওকে, আস্ক কোয়েশ্চেন্স রাইট অ্যাওয়ে, সো দ্যাট মানে এটা নিয়ে যাতে ডিলে না হয়, রাইট? বিকজ গোল হচ্ছে কাইন্ড অফ, আমি অলসো ট্রাইং টু শেপ দ্য গোল, আসলে ফাইনালি আমরা কি করব। বাট ফর নাও, কোয়ান্টাম এক্সপ্রেসে কম্পিউট করার পর you can actually extract the Hamiltonian for a system. Like, you provide the input files, you do computation, then you can extract the Hamiltonian. Using that Hamiltonian, you can compute some interesting properties. এখনকার সময়ে একটা কাইন্ড অফ কাটিং এজ ফিল্ড হচ্ছে topological insulator, and in different materials, the properties are called topological invariance. Okay, so you can calculate those Chern number or winding number. Those things you can calculate few things from the Hamiltonian itself. So that's kind of a goal. এখন to go there, আমাদের কিন্তু 1 মাস আজকে কমপ্লিট মানে পার হয়ে যাচ্ছে. We just have 2 more months. So we have to kind of speed up a little bit. যাতে দুই এক সপ্তাহের মধ্যে যদি আমরা হ্যামিল্টনিয়ান এক্সট্রাক্ট কিভাবে করে পেয়ে যাই, দেন হয়তো আমরা মানে ভালো কিছু করতে পারবো। লেটস সি। সো ইফ ইউ হ্যাভ দ্য
স্যার,
ইয়েস
হ্যালো
ইয়েস, আই ক্যান হিয়ার ইউ।
স্যার, আমার হচ্ছে এসএসএস ফাইলটাতে যা দেখাচ্ছিল ওইটা আমি আপনাকে ছবি হিসেবে সেন্ড করছি ডিসকর্ডে, একটু দেখবেন যে ওইটাতে কোনো প্রবলেম আছে কিনা।
Okay. It says you have the config file, could not resolve host name. Okay, I think I got it. So if you go to config file, host name should be the IP address. For example, here is this one. And port number should be 22. User should be your username, যে ফর্মে যেটা সাবমিট করেছিলা. Then identity file should be the private key. So এখানে এই টিল্ডার মানে হচ্ছে হোম ডিরেক্টরি. So if I type this command, you see users/Shahnur in Mac. In Linux, it will be /home/your username. In Windows, it could be something a little different. But when you see this tilde command, it means the home directory. See, this is the home directory. And since this is a defined symbol, so if you write tilde/.ssh/ the private key file name, then it kind of works. And here it says the error could not resolve host name. Host name, I okay. I think you need to restart your SSH কি বলে সার্ভিস, বিকজ এখানে কনফিগারেশনটা কারেক্ট মনে হচ্ছে। Do you know how to restart a service? Excuse me, guys. I need to just excuse me for a second. So I think you need to restart the SSH service. Okay, and then it should work. Try restarting it. Okay, I'll be back like quickly.
ওকে।
আপনারা সবাই কি এই সার্ভার অ্যাক্সেস নিয়ে নিছেন এবং মানে নিলে কি আরএসএ এনক্রিপশন ইউজ করছেন?
Yes.
সরি, লাস্টের কথাটা বুঝিনি।
হ্যাঁ, আমরা সার্ভার অ্যাক্সেস নিয়ে নিছি আরএস এনক্রিপশন দিয়ে।
ওকে।
হোপ ইউ ক্যান হিয়ার মি প্রপারলি। আমার ইন্টারনেটের অবস্থা
না,
খুবই খারাপ, সরি।
আপনার কথা শুনতে পারছি, লাস্টের দিকে একটু ফাজি হয়ে গেছিল। না আহ, না আমি হচ্ছে যে আমি এখন নেই, আমি ভাবছি হয়তো মানে আই ডোন্ট নো ওয়াই, এনিওয়ে আমি জাস্ট খুঁজতেছিলাম, এখানে বলতেছে হচ্ছে যে ED25519 প্রোটোকল হচ্ছে বেটার। আর মানে বেটার বলতে কি বোঝাচ্ছে আমি জানি না, দুইটা কথাই বলছে, ফাস্টার এন্ড মোর সিকিউর। সো আই থিঙ্ক ইট ডাজন্ট ম্যাটার, বাট মানে স্যার কি কিছু বলছিল যে লাইক নিউয়ার প্রোটোকল স্যারের সার্ভারে রান করে না বা এরকম কিছু একটা?
Hi guys, I'm back. So yeah, any Shonal, তুমি কি ট্রাই করেছো সার্ভিস রিস্টার্ট করা? I think I forgot the command. Restart Ubuntu. I think yeah, systemctl, system control, restart SSH. If you run this command, then it should restart the SSH service and maybe it will work. Try it. Okay, I can see new the restart SSH service. Try this command. Okay. Yeah, if you have it should work. If restarting করলেই কাজ হয়ে যাবে। যদি ভার্চুয়াল বক্সে চালাও সেক্ষেত্রে you can just restart, মানে stop the virtual box, start it again, or restart your computer. It should work. Okay. All right. So I have like multiple user setup for different purposes in the same kind of machine. So here, Quantum Espresso. So I have, okay. Here I have Silicon input files in ConLab SSH. So let me show you how you connect. So once we have that configured, you can open a new window, then click here, connect to host, remote SSH option. I think I showed it in the video that I tried to make. Here you can select any configured server. I'm going to select this one, ConLab. And now it's open. I can go here, open folder. I'm going to open Quantum Espresso, or I can just open the entire home directory. So yeah, like uh, I think like তোমাদের চারজনের মধ্যে দুজন কি করতে পেরেছো এই পর্যন্ত? হ্যালো।
আমি করতে পেরেছি ভাইয়া।
Okay, okay, great. Yeah. Okay, so at least একজন পেরেছে, that's good. সো তাহলে এক কাজ করা যেতে পারে, যাদের মানে প্রবলেম হচ্ছে বিভিন্ন, সেই ক্ষেত্রে উই ক্যান ক্রিয়েট নিউ চ্যানেল। What do you call it? You call it channel, right? So মানে ডিসকাশন চ্যানেল, যেখানে তোমরা নিজেরা নিজেরা ডিসকাস করতে পারবা, ইউ সলভ ইচ আদার্স প্রবলেম, রাইট? বিকজ আমিও অনেক সময় অ্যাভেলেবল না থাকতে পারি, বিকজ ইটস লাইক ডিফারেন্ট টাইম জোন। ওকে, but you can also like DM each other, I guess. Okay,
Creating a new channel would be better.
new channel. Okay, let's create it right away. So create channel. What should we call this channel? Discussion, brainstorm,
Sounds fine.
suggest names, guys.
Discussions, I think it's fine.
So what I didn't get what you said.
Well, discussion would be fine.
Discussions, create channel. Okay, so এখানে মানে যে কারো প্রবলেম, ইউ শেয়ার ইউর প্রবলেম স্ক্রিনশট, এন্ড মানে যখন যে অ্যাভেলেবল থাকে সে আনসার করবে, সো দ্যাট so that we kind of everyone is moving forward, moving along. Okay, no one is left behind. And general is mostly say for announcements and stuff. Okay, so once you have this open in VS Code, so it's the same location as here. If I do ls is a Linux command. It kind of lists all the files in that particular folder. So here I have all the input files are inside this input folder. So I can run the commands here in this terminal inside VS Code, or I can run them from here. So I'm going to do that. I can see all the contents of input file. So first I need to run the SCF computation. SCF means self-consistent field calculations. So MPI run number of processes, one process, pw.x. Input file is inside this input folder, SCF, and this angle arrow to show the to direct all the output to scf.out file. Okay, and if I press enter, then it says something. And if I do ls, there is no crash file. I just have one scf.out. I can do tail and 10 scf out. Tail means ওই ফাইলের লাস্টে যতগুলি লাইন আছে সেগুলি শো করবে, minus and 10 means last 10 lines, and I see job done written there. That means it ran successfully. If you want to run the NSCF file, calculations, just change the names. It took a little longer, but again, NSCF, a job done is fine. And SCF and SCF, then what do we run? So here I have a script written. A script, sometimes when you know the workflow, like exactly what you need to do, you can create a script like this. Okay, and then just run this script. It will do one computation at a time, right? প্রথমে SCF করবে, পরে NSCF, তারপর bands.in. You can copy this. It's also in my GitHub repository. If you go to GitHub, you can find Quantum Espresso. This is my account. Here you have scriptqe.sh. Okay, you can copy this file, edit it the way you need, and then try to run it. Now, in my input files, you see, I don't have any sudo underscore dir, in the control. Control name list, I don't have that. কারণ হচ্ছে আমার কোয়ান্টাম এক্সপ্রেসের জন্য একটা environment variable define করা আছে. So if you go here, Quantum Espresso, why is it taking long? Okay, and go to documentation, and is it in tutorials? No, it's in document input data description. Okay, go to documentation, input data description, pw.x. There you have all the, like, everything that's kind of defined in Quantum Espresso. You have all the list, like how we define controls, and in controls you can have these options. There you have sudo directory, this one. If I open this, here it says sudo directory is a character, and value of espresso sudo environment variable, or the location specified in the input file. So যেহেতু আমরা মানে কয়েকজন সার্ভারটা ইউজ করব, যেটা আমি করেছি, I defined the environmental variable. If I do echo, it shows opt sudo. So in your account, you can see the content of the bash rc file, and there you should have this line written. I think I have added that line. I think I have added all these lines so that you have the executables in your path. So if you don't have this line written there in your bash rc file, then you just need to add this. Okay. All right. So now we run bands. Okay, it's taking a little longer. Why is it taking longer? Let's see. Bands.in. I have different K paths. No, not this one. Okay, total 10 K path. So yeah, I think I need to explain how you write the input files, but let me just generate the graphs first. So then after that, after bands, you run bands post processing. So for that command, line 41, for that command, it will be bands.pp bands.x, I think. Yep. And then for density of states computation, you just run dus.pp file. using dus.x command. Okay, I don't have any error, I think. So it's all good. Then to plot it, there's a so after you run the computation, you need to figure out what the Fermi energy is. And let me show you in VS Code. So here you have this dus.dat. You can go there. Fermi 6.8 electron volts. That's the Fermi energy inside the dus.dat file. Or you can go to NSCF file and search for Fermi. So the Fermi energy is 6.84 here. Okay. And which is near the end of the file. So just, you need to copy that Fermi energy from here and then go to plotbands.gp and go to plotdus.gp. GP is GNU plot or new plot script. I can run this from here, I think. So GNU plotbands.gp, press enter, and then plotdus.gp, press enter. And if I do ls, I'll see two new files, PNG files. And here I have dus. And see, the range is not very good. If the range was 0 to 5, maybe you would see a kind of more details. In band structure, again, the range is not very good. It's -1 to 1. Maybe we want different range. So let's modify those files. So still -4 to +4 electron volts. And here, Y range should be, say, I don't know, 5. Let's try to run these commands again. Plot bands, plot dus. Yeah, now I can see more of those bands. And here I can also see the density of states. So here, this dashed line is called the Fermi level. And if you see, there's this density of state is in like how the density of state is on the Fermi level. It defines a lot of things about that material. You see, silicon is a semiconducting material, right? That's why there's a gap here, and there's like a slightly little bit of density near 0. Okay, and if you see the band structure, you see, there is no band crossing the Fermi level. On this 0 line, if you draw a horizontal, so this energy versus k path, here there is no band crossing this 0 line. And if you compare that with a different band structure that I have, here, if you draw a line, horizontal line, you see this band is crossing that line. So it's a metal for this band along a particular direction. Now you can write Python script to plot these and have all the band labels. So I mean path labels. I think I showed you in that video from materials project website. You can look for any material, let's say silicon. You have to log in. For silicon, let's try the first one. If you go to crystal structure, electronic structure, and this is the band structure and Fermi energy. So band structure is plotted from -5 to 9 electron volt. You see, I have E minus EF here in the plotbands.gp file. here I am plotting E minus EF on the like along y-axis. So 2 is basically the second column of the what is the file name of this file, bands.dat.gnu. Okay. So if you see this kind of similar, then that means your calculation is kind of correct. Okay. So last week's assignment was to generate the band structure and density of band structure. Now you also need to generate the density of states and try to plot it in Python. Okay. Because that if you can plot it in Python, then you can also do other computations using that. So to be able to plot in Python, I think you can use this XML file. Here you need to extract, but you'll need to extract this XML file, but it's kind of structured there. Maybe I'll show it in a future session. But you can try. All the information is in that XML file. Okay. So any questions so far? Now I'm gonna try to explain about these input files. But if you have any questions so far, you can ask. Okay. So about these input files, this AND control and system, these are called name list. If you go to Quantum Espresso input file description, AND control can have these kind of elements in it. Some are logical field, some are character field. And here I have defined, you need to define the calculation type, which is SCF for scf.in input file. For NSCF, the calculation type would be NSCF. And you see, I have this prefix here. Prefix is really important because the output directory you have there, using that prefix, it will create prefix here, silicon.save file folder, also prefix.xml file. And when you run the SCF computation, it will generate some data, put it in this output directory here, temp folder. And later on, when you run NSCF computation, it will access those files from there. So in NSCF and SCF, in all the files, you need to make sure that prefix and output directory is the same. Okay, they must be the same for all the computation. All right, and then you have iBrav is the Brevis lattice. So there are 14 types of Brevis lattice, right? So if you go here, that's for system iBrav. Go there, and you see 0 means free. Free means you actually specify the lattice vectors. That way it knows what's the structure, or you can specify 1, which is for cubic, and 2 for cubic but face-centered, FCC. Are you guys familiar with these Brevis lattice structures? Cubic, face-centered, body-centered, hexagonal.
Yes, the basic
Yes, sir.
ones.
Okay. Okay. If you have questions, we can probably cover it in for some future sessions. But the descriptions are here. So the important part is you get this right. If it's 0, you need to provide the lattice vectors. If it's 1, 2, 3, and you provide the cell parameter, it will compute the lattice vectors for you. Okay. There are some questions in the chat. Okay. Excuse me, guys. I'll be back. Okay, I'm back. So the reason I'm kind of taking break every like 15 minutes, so I'm cooking something, so I just need to monitor it like every 10, 15 minutes. It's almost done. Um, yeah, sorry about that. I mean, I have other things scheduled tomorrow, so today is the day to prepare my food. Okay, so then you have this cell DM, cell dimensions, which is 10 in this case, which is in Bohr unit. And if you go here inside a system name list, you have cell dimension. And here, as in, you can provide in Armstrong or in Bohr. So I can be from 1 to 6 is, I think, in Bohr unit. And if you provide ABC, cosine ABC, those will be in Armstrong. Okay. So the thing is, all the fields here you see here, you want to know the details, the way it's defined, you just go in the Quantum Espresso website, input file description, find that particular field, and then check the description. Okay, for that. I have some description written here. N-type, NT-YP, number of atom types, meaning in silicon, they're just silicon. But if you have a material, say bismuth solenoid, then it will be 2 types of material. Sodium NaCl, sodium chloride, salt. If you want to calculate for that, that will be sodium and chloride. So NTYP would be 2. NAT is number of atoms in a unit cell. It could be 2, it could be 4, it could be 14. Okay, so what is a unit cell? If you remember, we have tried to calculate the bands for phonons. So initially we had monoatomic chain, a single atom repeated in one-dimensional system. So there, NAT would be 1 because there's only one atom in a unit cell. For diatomic cell, one-dimensional, we have 2 different atoms in a particular cell. So NAT would be 2. Does it make sense somewhat?
Yeah, it does.
Okay.
Yes, sir.
And you can also get this information, I think, from the Materials Project website. Okay. So they sometimes use VASP, I think, which is kind of Quantum Espresso, but paid version. Things are a little bit easier there. So see, it says number of atom 8 here. It's cubic. So if you want to, you can also copy this from here. Okay, so it's a different system, different input file. For that, number of atom would be 8. You can copy that from here. It's cubic. And these are the cell parameters, 5.44. If you go there, so 5.44 in Armstrong, in Bohr is almost double. And okay, so then what are these E cutoff? E cut WFC. WFC means wave function. Is plane wave cutoff energy. And E cut rho is for the charge density. If you remember, we saw, so I have shared, I think, this link with you guys. So it's a Quantum Espresso kind of course from 2021. There, they talk about these limits, like how you set these limits. Um, Yes, good question. So the question that was asked by Alvi, from Metro's project, can we get the CIF file for a structure and then put that in Quantum Espresso? we can like you can get few things like the lattice parameter and their atomic position from the CIF file, but few things you need to provide. For example, these cutoff energies, they won't be there in the CIF file. The pseudo potential you want to use, that probably won't be there in the CIF file. Those are something you need to kind of specify. But the atomic positions will be there. K points, they won't be there in the CIF file. Okay. So I think there are Python packages, modules that you can use to convert CIF file to an input file, then add other fields that aren't there as you need. Okay. You can also, there's another website, Nomad Lab. So in Nomad Lab, you can search for a material. Let's see, silicon, SI, let's see. Okay, it says the entry type, single point, and VASP, geometry optimization. I'm just randomly choosing one. And there I can get inside. Where is it? You can go to files, and then you can go to in-car, pause-car. Yeah. So this is the file, POSCAR. You can convert like the parameters they used, they're kind of saved in this pause-car file. You can generate the input file using this pause-car file from Nomad Lab. That's also possible. Okay. So just download the file, and it's just few kilobyte. New window, open. So you see here, it says that I think this is the atomic position. This is the lattice vectors. So sometimes it's really simple, the files. Okay, but there are ways to convert or create input files from these previous calculations, CIF file like this one probably, or from Metro's project. Okay, the question was, for SCF calculation, the pseudo potential we download and place in the pseudo or the directory in the input file, is the directory already created, or should I create it myself? You had mentioned, okay, good question. So if you do echo espresso sudo in your account, in my server, you should see this output, opt/sudo. And if I want to see the content of that file, see, lot of pseudo potentials. For silicon, I think I have for silicon as well. I can search. Yeah, here. For silicon, I have this file. One pseudo potential is there. So if you need to use different pseudo potential, you can download that and try to upload it here, or send it to me. I'll put it there. Or you can create your own folder and specify the pseudo directory here in the input files. So the way you do it, input files equals /sudo. So if you do this, then you see I have input here, temp here, right? And the way I've written it here is /temp. Dot means the current working directory. So /sudo, yeah. No, I think, okay. /sudo means you have to create a folder named sudo and have it here like that. Input sudo temp, and your sudo potential should be inside the sudo folder. Okay, does it make sense? Answer your question. Okay, good. And if you want to use the default sudo potential directory, you can just comment that line. The way to comment it is, uh, this exclamation mark. Yeah, it's little, in Python you use pound sign, in C++ you use double slash, here is exclamation. I don't know why they don't use this universal um, symbol, but it's okay. Okay, then occupations fixed, it could be some like, you can go here again, occupation, and here it says these are the allowed occupation. You can try smearing, tetrahedra, or fixed. So depending on what type of material you have, you actually, use these. So for silicon, we know it's a semiconducting material. So it's, there's a gap in the band. So we use fixed. You can try other things as well and see what kind of bands you get. So this is what I want you to do. For the same silicon file, try these different options. For occupation, it could be smearing, it could be tetrahedra. Just change one parameter here, occupations, to smearing, and see what kind of bands you get, what kind of density of states you get. Okay, and try to save all those plots. So when you run Quantum Espresso, try to maintain a log file. So here I have run_log.md. MD because you can format the file, it makes it easier. So the material I've been working on, I have ran, I think, 8 run, and 8th time it was kind of, I think, 99% matching with the one we have in materials project website. So every time you run something, just add a line like this, create your own log file, and pound run 1, run 2 with a date maybe here, say 2025, 08, 09, August 9th, and then you write something that was done differently than the previous run. In the first run, you should mention as much details as possible so that you remember that what was done in the first run. And in the second run, what did you change? Okay, like when you experiment with the different parameters, this is how you do it. Okay, and convergence threshold is, so it's like 1.0, 10 to the power minus 8. They have this convention, they use D letter, not E. I mean, you'd think they would use E for exponential, but they use D. So this means the quantity they try to optimize. If the quantity is smaller than this number, then they stop the computation. Otherwise, they keep going. And mixing beta is a mixing parameter for SCF. I think is this mixing. See, here is alpha. Okay, let me just finish this SCF file. Then under atomic species name list, is it a name list? Probably. You have the name, silicon, a symbol name, and atomic mass, and the name of the pseudo potential. This file must be there in sudo directory defined here, or the global espresso_sudo variable. If it's not there, you'll see an error. Okay. Then to provide atomic position, you see there are 2 lines here. Why there are two lines? Because here I have NAT2, number of atoms in your cell. If you have 10 atoms, then you must provide positions of those 10 atoms. Does it make sense? So it must be consistent in a particular file. Okay, any questions? And for K points, so remember we plotted the band's energy as a function of K. So in one dimension, you have just Kx. In 3D, you have Kx, Ky, Kz. And the way these quantum espresso computes these, it uses a grid to divide the space, that discretize the space, right? So it will be say six, six division along X, six division along Y, six division along Z. And 0, 0, 0 is the center of the computation. This is the gamma point, they say. So if you go in materials project, you see this gamma. This gamma is the 0, 0, 0 coordinate, or this gamma, this gamma, this gamma, this gamma, they're the same. Okay. So as we go along, we'll learn more, but this is basically center of your reference frame or coordinate system, 0, 0, 0. Okay. Okay, so try to run and think. If you have any questions, I'll be back in a minute. Okay, I'm back, and hopefully there won't be any interruptions. Just turn off the oven, so it's all good now. Okay, so far any questions about the STF file? Okay, so I think it's also important that there are kind of multiple ways you can write the STF file. You can also have comma here at the end of each line. Comma is not necessary, but if you use one convention, try to be consistent, I guess. Okay. And then in an STF file, occupations is tetrahedra here, because it's recommended that for density of states, tetrahedra is kind of important. So these parameters you need to experiment with a little bit. So the way it works, the more you know about the material, the better you can configure your input files. So it's not just, if you're given a random material you don't know anything about, it will be really difficult to write the input files and get the right bands. So it's like some experiments, some theory, some computation. It's like back and forth. Okay. And one important field for the system name list is number of bands. Here I have 8 bands. The more bands you add, the longer it will take. The higher or smaller convergence threshold you have, it will take longer to run. Okay. So if you run it, say you want to test your input files in your own system before running it in the server, then you want to have a smaller number of bands, lower number of bands, and a higher threshold like 10 to the minus 5, okay, and less dense K grid. So in STF file, the K grids are little codes like 666, but in NSTF is 888. Let me show you the material that I have computed for the bands for. So here I have 2 different atoms, and the K point grid is 12, 12, 24, because along KZ, the length is kind of bigger. So I needed more points there. For cubic system, they must all be the same. Okay, so it's consider a cube that along z-axis is kind of longer. It's not a cube, it's a rectangle, or something like parallelepiped. So along z, if the length is longer, in to provide more grid points, so that the computation is kind of uniform, so that the steps between each grids is similar, comparable. Okay. And for NSCF, I have 22, 22, 32. Okay, so this NSCF and these configurations, it took 5-6 hours to complete the run in my server. So you see, things can take like a really long time. And after SCF and NSCF, you have the bands.im file. Here, no extra bands. I chose this NOSIM to be false. You can go here and check. So what is this? Symmetry is not used if true. Consequences: if a list of K point is provided in the input, it is used as is. Symmetry equivalent K points are not generated. And the charge density is not symmetrized. So it's like the way to optimize. Sometimes we want that, sometimes we don't. It's like, you see, there are a lot of different options, right? A lot, just for pw.x command. So it's really difficult to know all these and then starting the computation. The way, I think the better way to do it is, just start with something you have and then explore as you go along. Like if you need something, you can always Google and find which field is important, which kind of name list you need to modify. Okay, and then run the computation again. And we have the atomic species, we have the pseudopotential, and in bands, this is important. So it says K points, crystal B, 10 means there are 10 lines, 29 to 38, there are 10 lines. And this one says 000, 40. And see the lines after this exclamation mark, this is comment. I think I've said it before. And these are the labels of those paths. So what are these? Let me Brilliant zone. I think I have PDF quantum espresso. I think, yeah. So I think I need to share this file. So here, this talks about the Brillouin zone. So for simple cubic lattice, the lattice vectors are, they have the same length along all direction, x, y, z. This one is along x, this one is along y, last one is along z. And the reciprocal lattice vectors are b1, b2, b3. Do we all know how to calculate this reciprocal lattice vector?
Yes, but for the simple structures like BCC, FCC.
Okay. For any system, there's a formula that you can use to compute AB, B1, B2, B3. I think in Wikipedia, we have, where's the formula? Yeah, this is the formula. So to compute B1, you do A2 cross A3, and there's a factor in front, twice pi over the volume of the cell, then you get B1. Then B2 is like A3 cross A2, B3 is A1 cross A2. And the volume is this formula. You have ABC, A1 dot A2 cross A3, you get the volume. So that's how you can compute B1, B2, B3. Okay. And for cubic system, you see it draw. So you see Kx, Ky, Kz, this unit cell is in reciprocal space, meaning along Kx, they have plotted B1, along Ky, they have plotted B2 and B3. The center is gamma, which is the 0, 0, 0 coordinate in K space. This is also the Fourier space, not the coordinate space, the momentum space. Okay. And there they define different paths along ky. From gamma to ky, we have gamma and x. That's the direction. Meaning, if you see here gamma x, right? It means gamma is the center. From there, go to x, right? And for x, the coordinate here is 0.5, 0, 0.5. That's the dimensionless coordinate they use. So that's basically going from gamma to x. You can always, I think, find those coordinates. But let me just finish. You can go gamma to x. You can go gamma to m. But so they went from gamma to x, then x to w. Do we have any w here? No. But we have w there. I think there is something needs to be modified here. So for this particular cell, the paths would be from gamma to x, then from x to any of these two, say x to m, then it could be m to x1, then x1 to gamma, then gamma to r, and also r to x and r to x1. What are the possible paths in that Brillouin zone? Does it make sense? So in this file, you can see all the possible paths. For this system, hexagonal system, you see we have gamma, A, L, M, K, H. Can anyone tell me what will be the possible paths here? Start from gamma. Gamma to M, that's one path. And then from M, we can go to K or L. Yeah, keep going, anyone. You have to, I think someone texted. So gamma to M, M to L, L to A, gamma to M, M to L, L to A to H, yes, H to K, and K to gamma again. Yes, this is true. But we also have gamma to A, right? So the way we specify is kind of up to us, but we try to make it continuous, like gamma to M, then M to L, L to A, then A to H, or A to gamma. Okay, it's like we try to make it continuous so that our bands that we generate, they look continuous, because here along this K path, we have gamma to, let me show you in Metro's project website. So we have gamma to X, right? So that's one path. What we see, say here, gamma to X. Okay, then X to W. I think this is a different cell. This hexagonal, tetragonal lattice. Yeah, just need to find that particular cell. Let me show you just, for this case, these are the path like along different direction. So if you don't organize it like the way it is, in this continuous way, then this graph won't look smooth. It's not a 2D graph, it's basically multidimensional. Gamma to X, one direction, X to W could be perpendicular, could be at an angle. Okay, so that's why they look continuous, these lines, because we chose continuous paths. Does it make sense somewhat? Okay, so that's how we need to choose. So iBrave টা কি আছে তার সাথে ম্যাচ করে you need to kind of define the paths. Okay. Yes, for different crystal structure, path will change, exactly. But there are 14 types of Braves lattice. So let's take a look at the last one. -12, and this one is 12. So this one is what is this? 11. So এখানে যে কয়টা ডিফাইন্ড আছে iBrave এর বাইরে কিন্তু হওয়া পসিবল না, এর বাইরে হলে এরর দিবে। So if I go to iBrave, you see 1 0 1 2 9 -9 91 is there, 12 13 14 triclinic. Okay, so এর বাইরে হওয়া পসিবল না। পার্টিকুলার iBrave এর জন্য k path গুলি কি হবে, you just need to define that. Okay, so once you know the path, you need these indices. So এই ইন্ডেক্স নিয়ে একটু পরে কথা বলছি। এই 40 যেটা বলছে 40 40 40, it means from gamma to x, এই প্রথম যে 40 লেখা আছে প্রথম লাইনে, gamma to x ডিরেকশনে 40 k পয়েন্টস থাকবে, 40 ডেটা পয়েন্টস থাকবে। তুমি যে ডেটা ফাইলটা পাবা along gamma to x 40 ডেটা পয়েন্টস। সো প্রথম 40টা হবে gamma to x, তারপরে gamma to w again 40, w to k 40, so লাস্টেরটা l to k 40 পয়েন্টস। এখানে যদি let's say 50, so l to k 50 পয়েন্টস, k এখানে আসবে যখন জাস্ট 40 লেখা, বাট k এর পর আর কোনো লাইন নাই, so it will just add 1 point for that k. Okay, so that's the structure of the bands dot, I think bands.dat. Yeah, if you go to bands.dat, here I have 8 bands and number of k points 361. If you count these, so we have 40 40, right? There's the 80, another 40 120. If you count all these, you'll see it will be around 360. But one is I think because last point is just added there. Is it so there are 10 lines, 40, it should be 400. I don't know why it's 360. Is it? I think we have some repetition somewhere. So this is the coordinate 0, 0, 0 as specified here. And then from 0, 0, 0, it will go to 0.5, 0, 0.5, that direction. So you see, point 025, 0, 0, 0, 0.05, and then it will keep going. It should go to point. It's difficult to go through this file and find the points. Maybe it's moving along. Oh, okay. So, okay. So the coordinate used here is in dimensionless unit, but the coordinates used here, they have the dimension of inverse Armstrong. Okay. So that's why they don't match up directly. But yeah, I'm gonna explain what are the relations between these. But except for that, do you have any questions? For the possible k-point path, should I use quantum espresso input file generator to do it or do it manually? I think you can try both. See which one is which one suits you, how many points you want. If you know the length between along different path, for example, here in the graph, you can see along gamma x, it's kind of and between gamma x and xw, the length is different. So maybe you want more points along gamma x and less points along xw. So then what you do, gamma x 40, xw maybe 30. And W to K, that's even smaller, maybe 25. Okay. So what will happen in this way? The thing is, total number of K point doesn't matter, but along gamma X, we have 40 points. A longer distance, you need more grid points. Shorter distance, with smaller number of grid points, you can get the distance between each grid point can remain the same. Okay. Or I think I need to, it's better to share my iPad screen and explain that. But, different distance, different number of K points, that will make the graph smoother. If you have more, along gamma X, you have 40, along XW, you have 40, then along gamma X, like less dense the K points are. Okay. So to optimize the computation, total number of K points along gamma to W is 80, 40, 40. If you distribute it uniformly, then maybe along gamma X you can have 50 and XW you can have 30. Total number is the same, but you distribute the mesh in a way so that all the points are equally separated. Does it make sense? Okay. Yep. Okay, so I guess that's kind of the way you run, generate the bands and density of states. So assignments would be the same, generate the bands and density of states, and I think I need to show you the relations between these K points and these indices and these indices. I think I have, let me check quickly. I have the documents. Just a minute. it's not here. Okay. Yeah, electronic bands. Paperworks. Okay, I can't seem to find that file. So what we need to understand how this conversion works from this coordinate system or this unit, which is dimensionless unit, to the units used here in this file. Okay, and so how many of you are kind of good with Python code? Like you consider yourself kind of good so that you can read this file bands.dat and extract the coordinate and the bands. So remember n band was 8, that's why you have -5 to 9.9, there are 8 bands. So for each coordinate point there are 8 bands, 1 2 3 4 5 6 7 8. That's why in this graph there are total 8 bands. If you change the range, you'll see all those 8 bands there. Like for at each point there are 8 kind of dots in this graph. Okay, so that this can also be a project, like just to try. So so let's try to have 2 projects this time. One thing is that everyone should try to run this in their own account. তুমি নিজের local machine run করতে পারো, it's fine. Okay. But in future heavy computation জন্য, if you need the server, you can submit the form and have the access. So try to generate this graph, band structure and density of states, and in the bands.dat file, you need a way to parse this file and extract the data. So how do you do it? You skip the first line. You need to read this file line by line. So how to read files in Python? Maybe just Google that up. It's easy. Just open the file and read the files, and then read the second line. That's the K point. So 3 numbers, and next line is 8 numbers. So it's like this is the, if you have so you also need NumPy to kind of efficiently do this. Let me quickly show you how, like a schematic way of doing this. Okay, read.py, and that will be all for today's session. Import NumPy as np, and open for the name bands.dat as f.read line, so this is simple Python script. I want to see what output do I get. cd quantum espresso silicon, and I have this py file. What is it? read.py. If I run this, I just see this line. So what is it doing? It's reading this, opening this file bands.dat, and so we can do this. We can f equals open the file and then read it like this. let's see if I get the same thing. Yes, I get the same thing. So F, so if we just run this command open, it will open the file, and F will be the object on which we can run these methods. Read line is this method, right? So a good thing about VS Code, if you just hover over a method or a class name, it will show you some kind of description, like how it works. And it returns a line. In the first time, it reads one line at a time, so it returns the first line. And I can print that line, see it here. If I run this command again, I can see, two lines, first line and the second line. And but you see, when you open a file, it's important that you close it. But excuse me, but when we are doing it this way, F equals open, and then line by line we're doing things, we're not closing the file. It's important that you close it. You can run f.close manually, and then all is good. Or you can do this with open the file name as F, then you don't need to close the file. So with দিয়ে করলে যা হবে, when it exits this block, so Python after this colon, whatever you write with an indentation is called a block. Okay. Block of code. So when it exits this with block, it will close the file automatically. That's the advantage. You can read one line at a time, or you can read all the lines using this command at once. And if I run, so I don't have anything here, all things is commented, just 3 lines. It reads all the lines and just prints it in the terminal. Okay. And we want to so let's go here. So print line 0, 1, 2. So I want to skip this. So I'm reading all the lines, but I'm just printing line 0, 1, and 2. You see, line 0 is something we don't probably need. Line 1 and line 2 are important. So what we'll do, we can create a for loop for I in range if we say 10, then it will go iterate 10 times. And this pass is a way to end the block. It doesn't do anything, just a flag. We can have k point list and bands, e-bands list. So I can do line start from 1. I equals I. So you can see what I it is. I, step size, let's say 2. So if you want to know what is doing the range function, it says start index, stop index, step size. We start with 1, stop index is 10, and step size is 2. So that's K, and E, the energy is I plus 1. Does it make sense? The first element, when I is 1, we get the K point. When I is 1 plus 1 or 2, we get the energy. And we just need to save them. Dot append. We can do dot split. Okay, let me just K and ebands.append e, and we can print kPoint afterwards. So clear the screen, run the command, and we see I equals 1, 3, 5, 7, 9. And when we print, let me just print kPoints, we see we have 0, 0, 0, then 0.025, 0, 0, 0.0500. So exactly what we have here, right? Any questions? These are the kPoints. And then for, yeah.
স্যার আমরা এই ভ্যালুগুলো তো জাস্ট ব্যান্ড ডটস ডিএটি ফাইলেই দেখতে পারতেছিলাম, আমি এইভাবে কোড করে আউট কেন করতেছি?
গুড কোয়েশ্চেন। সো এখানে আমরা কিন্তু প্লট করার জন্য ইউজ করলাম হচ্ছে নিউ প্লট, রাইট? সো নিউ প্লট যখন প্লট করে সে ইউজ করে bands.dat.gnu। সো এখানে জাস্ট এক্স অ্যান্ড ওয়াই কোঅর্ডিনেট দেওয়া। এখানে যেমন দেখো গ্যামা টু এক্স একটা প্যাথ দেওয়া আছে, রাইট? যদি নিউ প্লট দিয়ে প্লট করি, বাই ডিফল্ট এই প্যাথ ইনফরমেশনগুলি থাকে না ওখানে। উই জাস্ট সি দ্য ব্যান্ডস, লাইক একটা রাফ প্লট টু সি হাউ ইটস ম্যাচিং অর নট। যদি প্যাথগুলি আমরা চাই, হুইচ ইজ ইম্পর্টেন্ট, যখন আমরা লাইক সে একটা পার্টিকুলার ম্যাটেরিয়াল আছে যেটার ইউনো এ ডিরেকশনে ওইটা মেটাল, বাট বি ডিরেকশনে এটা ইনসুলেটর, এরকম ম্যাটেরিয়াল কিন্তু আছে, লাইক অ্যানাইসোট্রপিক ম্যাটেরিয়াল, ডিফারেন্ট ডিরেকশনে ডিফারেন্ট। আবার একটা পার্টিকুলার অ্যাঙ্গেলে যদি কাটা হয়, দেন ইট কুড বি ডিফারেন্ট অ্যালং দ্যাট পার্টিকুলার ডিরেকশন। ওকে, সো এই জন্য উই নিড টু নো দ্য কে প্যাথস, কোন দিকে কোনটা মানে ব্যান্ডগুলি আছে। সেই ইনফরমেশনটা এক্সট্রাক্ট করার জন্য উই নিড দিস bands.dat। নিউ প্লট এখান থেকে প্লট করে না, নিউ প্লট প্লট করে হচ্ছে gnu ফাইল থেকে। ওকে, দ্যাটস ওয়াই we'll need to use a Python code, or we can do it manually, which is something probably we don't want to do. Hundreds of lines you have to do multiple times. It's better to write a script that will do it for you. Okay, so যদিও আমাদের গোল হচ্ছে ফাইনালি get the Hamiltonian and compute some topological invariants, but along the way it's your chance to kind of polish these skills, Python skill, other computer skills, or other some theoretical knowledge. Okay, মানে what we encounter as we go, we'll try to explain a little bit. Okay, does it make sense somewhat?
হ্যাঁ, মানে আমরা একটা ম্যানুয়ালি কল পেস্ট করতে পারতাম একটা নতুন ফাইলে, বাট জাস্ট অটোমেট করতেছি ব্যাপারটাকে ইটারেটিভ ফর লুপ ব্যবহার করে।
Exactly, because you'll run this SCF and SCF time, I don't know, hundreds of times. Okay, to like before you get it right, maybe deep for like complex material. For simple silicon material, maybe 5 থেকে 10 বার রান করলে হয়তো খুব ভালো ব্যান্ডস ডেন্সিটি অফ স্টেট পেয়ে যাবা। সো যদি 10 বারও যদি হয়, তখন কিন্তু অটোমেট করাটা বেটার, because it will read the file, give you the K points and everything, and you can plot it, analyze it, and you know that's really useful. So then we can bandsটা corresponding bandsটা কি এখানে দেখাচ্ছে, and then if we print K point 0 bands 0, then what it will show, why do we have 1, 2, 3? And I think I can, oh, I have these lines, that's why. Okay. Now, after the loop ends, we first entry is the K point, second entry is they are the bands. But Python কিন্তু different data types আছে. If we want to check the data types here, because we want to plot it, right? Data types, দেখার জন্য just type command is enough, and if you see, it will be string. But to plot a graph, we need numbers, so we need to convert them. Plus, so this entire thing is there as a list. So what we need to do, we need to run this split command. It will split. So all these bands.dat. So these values are separated by space. So when you run this split method, that will get rid of all the, you know, all the spaces and give you just the numbers, but as a string. Okay, so you see here, we don't have any commas, right? But if I run it now, you'll see I have comma. So now the format is a little different. I have individual element, but there's a comma in between. Now we need to convert these from strings to numbers. So how do we do this? We can do it here right away. Fastest way is probably this. Float ij for j in k. This is called list comprehension. Let me just type the name. I think I'm okay, shortcut. I forgot the spelling. Too bad. Okay, so j, it could be j in e. So that way it will convert. So it's a shortcut way of writing a loop. Okay. And if you do that, you see now all are numbers. And if I check, zero is a list, 0, first element, that's number, float. Now I can plot it. So instead of running 10, let me run it for 100. And I have 100 different bands saved, and now I can plot it. To plot it, I need to import matplotlib.pyplot as plt.plot. We have k point comma e bands, right? And plt.show. Let's see what we get. So X has 3 columns, but Y has 8 columns. That's the problem. This k point must have only 1 column. So the way to do it is k norm. I think let me just show you the fastest way to do this. So the way to do it, map lambda kk I think np.sqrt kk 0 squared plus kk 1 squared plus kk 2 squared. Then the square root k point and k norm list of this k norm. Let's see if it works. It worked, but why didn't I see uh, any graphs because I'm running it in a server. So যদি সার্ভার না হয় আমার মানে কম্পিউটার হতো তাহলে গ্রাফটা দেখাতো, যেহেতু সার্ভারে তাই আমাকে plt.save ক্লিক করতে হবে, bands py.png, Python থেকে bands. If I run this, it should generate bands py. You see, we see some lines, right? And here, if we increase this to 300, let's see. Okay, we're getting something. Now, we need to read all the lines, then we get the graph exactly like this. Okay, so that's one of your assignment this time. So you have the code. I can share this file. So modify this file, try to understand how I have done it, and if you have questions, text me lambda function map inside map. Okay, so you can break down these steps like এখানে যে লাইন 50 এক লাইন যেটা লিখলাম সেটাকে ফুললি ডিটেইল ভাবে লিখতে গেলে it could take I don't know 5 lines. So খুবই কম্প্যাক্ট ওয়েতে করা যায়, like this, in this way. So yeah, I know you have questions. So try to explore this file. So this time you have homework or assignment. One is run QE and get bands and DOS, density of states. Number 2, extract data from bands.dat file. Okay, that's the homework. Yep. And I wanted to explain the DOS today and maybe give you a paper to read, but সবারই পাইথন স্কিল একই রকম না, so that's why you need to probably slow down. But যেহেতু এই কোর্স কিন্তু is not a regular classroom course, right? So যাদের পাইথন স্কিল ভালো, you can do this homework in 1 or 2 days, right? And then text me যে এটা করা হয়ে গেছে, then I can instruct you to do something else. So সবাইকে একই স্পিডে যাওয়ার প্রয়োজন নাই, ওকে? মানে you don't like যারা পাইথন নতুন শিখছো ওরা এখানে একটু টাইম দাও, আর যারা এক্সপার্ট ওদের জন্য I have something more. Okay, does it make sense? সবাইকে একই স্পিডে যাওয়ার প্রয়োজন নাই. Okay, so you need to keep me updated about your progress like along the week. তোমাদের নিজেদের এক্সাম বা পড়াশোনা আছে, I understand, but যখনই হয়ে যাবে একটা অ্যাসাইনমেন্ট কমপ্লিট, text me, I'll give you a new assignment because 2 more months we need to kind of get to the point so that we can extract the Hamiltonian and get to calculate some topological invariance. That's something I'm really interested in. Okay. Okay, so yeah, that's it for today. Do you have any questions?
স্যার আজকের লেকচার রিলেটেড না, এমনিতে আপনার সার্ভার সম্বন্ধে একটু জানতে চাচ্ছিলাম, মানে এটার হার্ডওয়্যার কেমন
Configuration?
স্পেসিফিক? জি স্যার।
Okay, so server CPU is not powerful because most work is GPU oriented. GPU হচ্ছে NVIDIA RTX 4090. So VRAM 24 gigabytes and CUDA core I think 16,000. So powerful enough, I guess. But just a single GPU.
Yeah. Up to 4090. Yeah.
Yes. I didn't hear you.
না স্যার এটাই।
System RAM, I think no, 32 gigabytes. Not a lot, but kind of works. Our CPU core 6 core 12 thread. CPU is not very powerful কারণ purpose ছিল GPU based computation. So yeah. Any other questions? Okay. So silicon example
না
যদি
স্যার আমি
yes.
আমি ফর্মটা মাত্রই ফিল আপ করলাম, জাস্ট
Okay, okay.
একটু টাইম পেলে ইয়ে করব।
আমি মিটিং এর পরে মেবি হাফ এন আওয়ার, মানে আমার এখানে 12টা বাজে, সো আমি লাঞ্চ একটু আগে করি, সাধারণত হয়তো লাঞ্চের টাইম হয়ে যাচ্ছে, সো আমি করে ফেলবো। প্লাস সিলিকন এক্সাম্পল যদি কমপ্লিট হয়ে যায়, দেন হোয়াট আই উড ওয়ান্ট, ওই যে টপোলজিক্যাল ইনভ্যারিয়েন্ট কমপ্লিট করার জন্য যে মেটেরিয়ালটা আমার মাথায় আছে, সেইটা নিয়ে কাজ করা যাতে তোমরা শুরু করে দাও। হ্যাঁ, like generate the bands, like play with it, like change some variables or input parameters, see what you get, right? You need to be comfortable with all this. So server তোমাদের you can use the programs like pre-compiled Quantum Espresso executables, but you won't be able to install anything new. যদি কিছু install করতে হয়, you inform me, I'll try to install that. Okay, and what else? Yeah, so আমরা কয়েকটা ম্যাটেরিয়াল হয়তো কমপ্লিট করব, আর সবগুলোর জন্য আমরা চাইবো যে হ্যামিল্টনিয়ানটা এক্সট্রাক্ট করার জন্য, সো দ্যাট ইউ আর কমফোর্টেবল। ওকে, অ্যান্ড অলওয়েজ মেইনটেইন এ নোট, লাইক একটা লগ। ওকে, 3 homework 3 is maintain a log file for each material in a server, or um, to monitor your progress. Okay, রিসার্চের সময় কিন্তু মেইনটেইন এ লগ বুক ইজ রিয়েলি ইম্পর্টেন্ট, লাইক খুবই সাধারণ ডিটেলস, বাট ইউ ওয়ান্ট টু হ্যাভ ইট লগড। আমি যখন ল্যাবে কাজ করি তখন লাইক সে একটা মেটেরিয়ালের মধ্যে কয়েকটা ওয়্যার লাগানো হয়েছে টু মেজার ইস ট্রান্সপোর্ট কোএফিসিয়েন্টস, সো ওদের যদি কন্ট্যাক্টটা কিভাবে লাগানো হয়েছে, দোজ আর অলসো ইম্পর্টেন্ট। Was there any gold deposition or not, or platinum or not, or was it etched in some acid or not? এগুলি খুবই ইম্পর্টেন্ট ডিটেলস। ওকে, প্লাস থার্মোকাপল প্রোফাইল কেমন ছিল, was it good or not, টেম্পারেচার ক্যালিব্রেশনের সময় কোনো প্রবলেম হয়েছিল কিনা, এই সমস্ত ডিটেলস আর ইম্পর্টেন্ট। অনেক সময় ট্রিভিয়াল মনে হয়, বাট when you open up the logbook after 1 to 5 years, you see, okay, I don't remember what it was. Okay, try to list as much as possible in a log file. So yeah, সিলিকনটা যদি হয়ে যায়, মানে যাদের কমপ্লিট, try to do this in Python, just one file. Future হয়তো তোমরা অন্য কিছু করবা, but if you have this idea how to extract data from the bands data, then you'll be able to do other things by your own, like by yourself. So সিলিকনটা যদি হয়ে যায়, I'll give you new material and you write your own STF file, like গুগল করে ইনফরমেশন খুঁজে বের করে, or materials project থেকে, or CIF file থেকে data extract করে, you'll try to run write the own file by yourself and run the program, get the bands, match it with the materials project website. Okay, yeah, সো মানে সবাইকে একই স্পিডে যেতে হবে এরকম না, কারোর সাথে কারো কম্পিটিশন নাই, জাস্ট ট্রাই টু স্পেন্ড টাইম রেগুলারলি, লাইক ফিউ আওয়ার্স পার উইক, সো দ্যাট অ্যাট দ্য এন্ড অফ দ্য কোর্স ইউ হ্যাভ সামথিং টু শো ফর। প্লাস আরেকটা জিনিস যে আমি আই থিঙ্ক গ্রুপে জিজ্ঞেস করেছিলাম, ডু ইউ হ্যাভ সাম স্কিল অ্যাবাউট দিস লেটেক ইন ওভারলিভ, অ্যাকাউন্ট আছে কিনা? সো এটা যেটা করব, প্ল্যান হচ্ছে সাম ডিফিকাল্টিজ দ্যাট ইউ গাইস কুড ফেস, সাম ইনস্ট্রাকশনস, এটা আমাদের একটা লেটেক ফাইলে আমরা কম্পাইল করব, সবাই এখানে কন্ট্রিবিউট করবে, মানে যা কেউ কম কেউ বেশি। সো সুবিধা হবে কি, আফটার দ্য এন্ড অফ দিস প্রোগ্রাম, in 2 months we should have one, like something to show for that this is what we have done, right? এখানে তোমাদের গ্রাফগুলিও তোমরা করতে পারবা, আপলোড করতে পারবা। সো প্রথমে সিলিকন দিয়ে সবাই ট্রাই করো, দেন হোপফুলি 4জনকে 4টা ম্যাটেরিয়াল দেওয়া হবে, কিছুটা হয়তো ইনসুলেটিং, কিছুটা সুপার কন্ডাক্টিং, কিছুটা আই ডোন্ট নো টপোলজিক্যাল ম্যাটেরিয়াল, ডিপেন্ডিং অন ইউর প্রগ্রেস। সো আমরা সবকিছু এখানে হয়তো কিছু না কিছু ইনক্লুড করব। ওকে, পাবলিশেবল হবে কিনা আই ডোন্ট নো, বাট ডিপেন্ডিং অন লাইক হাউ মাচ ইউ গাইস ক্যান মেক প্রগ্রেস, এখানে তোমাদের নাম থাকবে, আহ, মানে কে কোনটুকু কন্ট্রিবিউট করেছে সেটা থাকবে, প্লাস ওই গ্রাফগুলিও এখানে থাকবে, হয়তো আমরা ইনপুট ফাইলটাও ইনক্লুড করব। ফর এক্সাম্পল সি এখানে এইভাবে লেখা যায়, লাইক ইউনো ইনপুট ফাইলটা এক্স্যাক্টলি তোমার কি ছিল, ফাইনাল ইনপুট ফাইল। হ্যাঁ, এখানে লিখে দিবা এইভাবে, সো দ্যাট নেক্সট টাইম যদি নেক্সট ইয়ার আমাদের এই PWF আবার রান হয়, those people will know your names and your contributions. Okay. Plus, I will also have something. Okay, we have done this last year, and it will be easier for me as well. Okay. So program কি হবে future, I'm not sure, but if we do this in this way, we'll have something to show for. তোমাদের সিভিতেও তোমরা লিখতে পারবা যে আমরা এই কাজগুলি করেছি, and this is what we have. হয়তো আমরা একটা PDF গুগল ড্রাইভের মাধ্যমে লিংক শেয়ার করতে পারবো হয়তো। So you can have that link in your resume that this is what I have worked on, and আমার কন্ট্রিবিউশনটা ওই ডকুমেন্টে ওখানে লিস্ট করা আছে। Okay, does it make sense? Like you can use it in many different ways, but you have to work like hard regularly. Okay. If you have Overleaf account, you can send me your account information like email address so that I can add you to this Overleaf project. Plus type করার সময় কিন্তু it's like sometimes it's a lot of things to type. You can use AI to do it for you a little bit. ChatGPT or আর কি আছে, Kimi or DeepSeek, you can give some information there and ask the ChatGPT, a chatbot, to generate the LaTeX code for you, and copy paste it here, see if the things are okay or not, and then modify it yourself, okay, to make it efficient. এখানে কোনো রেস্ট্রিকশন নাই কিন্তু যে আসলে কোনটা ইউজ করতে পারবা কোনটা পারবা না, ইউ ক্যান ইউজ এনিথিং, বাট দ্য থিং ইজ স্পিড আপ দ্য প্রসেস, ইউজ AI whatever. Does it make sense? Excuse me. Okay, so I guess that's it for today. Let me stop sharing my screen and stop recording. If you have any questions,
ম্যাটেরিয়ালের আরেকটা ওয়েবসাইটের কথা বলতেছিলেন।
Materials Project, Nomad Lab,
ইয়েস, মানে ওইটা কি লাইক ওপেন সোর্স প্রজেক্ট এরকম?
ওখানে লাইক অনেকে বিভিন্ন ধরনের কম্পিটিশন করে, তারা ওদের কম্পিটিশনটা ওখানে আপলোড দেয়। হ্যাঁ, মানে ওদের র ডেটা, সামটাইমস ইউনো ফাইনাল ডেটা ফর দ্য ব্যান্ড, সামটাইমস দ্য গ্রাফস or the input parameters they used. So it's kind of, it's open source, yes. Um, so far I've seen you can access almost anything there. Okay,
বাট
so
মানে দেয়ার মাইট বি রং থিংস টু।
yes, মানে ওরা যেটা করেছে ওদের ডিসক্রিপশনে ওটা আপলোড করেছে। ইজ ইট ইউজফুল টু ইউ অর নট, ইটস আপ টু ইউ। ইউ চেক থিংস, ইফ ইটস ইউজফুল ইউ ইউজ ইট, ইফ ইটস নট ইউ জাস্ট ট্রাই সামথিং এলস। ওকে, এটা পিয়ার রিভিউড কোনো মানে ডেটা সার্ভার না, সো there could be things that are not entirely correct. Okay, সো এই লিঙ্কগুলো আমরা ওই ওভারলিফে অ্যাড করে রাখবো যে দিস আর দ্য ওয়েবসাইট উই হ্যাভ ইউজড। ওকে, এনি কোয়েশ্চেন্স?